the Sridhar Kumar is here to continue with his presentation from the morning. And this time the topic is Introduction to Additive Manufacturing Technologies. Sridhar sir, we had a response like one person was stating that the presentation was quite good. Mr. Mukesh Kumar Sharma, he had given a feedback that the presentation was very good. So I think I can hand it over to Sridhar sir. Sir. Sir,
could you able to hear me?
Yes, sir. Yes, sir. It is audible.
I can able to see the presentation also,
yes,
right?
Yes, sir. That is also very clear.
Thank you, madam. Thank you.
Thank you, sir.
Yeah. Good afternoon. Good afternoon, everybody. Probably in the morning session, we have seen about the basic technologies behind various additive techniques. And now we will see in depth about some of the technologies which are largely used in industry for various applications. You can see here here on technology based, you can see the material extrusion. Basically, we call it as fusel deposition modeling. One of the familiar additive technology largely used by industry for various application, specifically from automobile sector to the level of aerospace. This particular technology, fusel deposition modeling, generally we call it as FDM, is playing major role. Stratasys is the company which is producing FDM based machines, which were widely accepted by industries. And recently, a lot of tabletop FDM machines also available in the market. A sharpboard kind of thing, or few example for tabletop machines. Even in India, a lot of small-scale manufacturers started producing tabletop FDM. Generally, the 3D printing, 3D printer, that term was derived from this particular technology because it's looking like as a printing mechanism. The other thing is the VAT polymerization. Stereolithography is one of the oldest technology and well known, comes under this. It is basically resin based material which should be cured by laser energy source. So stereolithography and then the digital light processing, DLP generally we call it as. So these two comes under this. Stereolithography is having wide acceptance almost in all the industries. Starts from automobile, medical, aerospace, and consumer goods. And this particular technology could able to produce even patents for investment casting, as we have discussed about the same in the morning. And the third thing is a binder jetting. BJ generally we call it as. This is the kind of technology where the powder particles will be bind together by using the binder. And is the powder bed fusion, selective laser sintering for plastic. SLS generally we call it as. DTM is the one of the company which was the founder. The technology owned by DTM, later on taken over by 3D Systems. So the next thing is the selective melting, which is pertain to metal additive manufacturing, where the laser will melt the metal particles and merge together. Whereas in selective laser sintering is also kind of same SLM only, but here the raw material would be plastic powder, nylon or glass filled nylon kind of thing. And electron beam melting, again same powder bed fusion and multi-jet fusion. This all thing, the raw material would be in a powder form and would be spread over a build platform. The energy source will come from the top and fall over the build platform. So the energy, for example, if it is a laser is the energy source, it should be scanned by the 3D model, whatever we are giving as input. And according to the profile in the pod, laser will scan over the build platform. So wherever the laser falls on the powder, that area, the powder will fuse and merge together. And rest of the area, the powder would be in a powder form itself. So this is generally called as powder bed fusion. It's fusing the metal powder or a plastic powder and giving opportunity to merge together, either by polymerization or in the metal case, it's a welding process, laser welding process, generally called it as. Electron beam, the energy source is different. The first two, the laser. The third one is the electron beam. The multi-jet fusion is something different that we will see while the topic comes. And another technology is the material jetting. It is passing the material through jets at high pressure. There are three kinds: material jetting, nanoparticle jetting, and drop on demand. Material jetting, the material will be in a polymer, in a liquid form, which should be, holes, jetting holes over the build platform, and would be cured by the, hello, yeah, cured by with support of line. And the nanoparticle jetting also same. Drop on demand is something like wax printing. And next thing is a direct energy deposition. There are two again. One is laser engineering net shape. That is basically energy source would be used as laser. The energy will. I think while presenting the technology in depth, you will see about it. Electron beam additive manufacturing, EBAM also. And the last one is the laminated object manufacturing. Sheets would be cut according to the profile in the 3D model and merged together, joined together. So these are that is generally called as LOM. So there are, you can see under 7 category, almost most of the additive manufacturing technologies can be included. And let us see one by one now. Yeah, this is a little bit difficult to go through because of the small screen. And this same thing only, and you can see some of the companies whatever overall producing. For example, SLA overall companies for 3D systems, Form Labs, and Cubes. Like that, even in DLP you can see Envision Tech, and CDLP you can see Carbon, Envision Tech, and FDM you can see Stratasys, Ultimaker, Markerboard, Jotrax, like Printboard kind of companies, Markforge and all. And a multi-jet fusion MJP, generally Stratasys and Envision Tech is there, and nanoparticle jetting XJet, and DOD you can see Solidscape, and BJ binder jetting you can see Voxel Jet X1. The companies who are all producing the machineries, and a multi-jet fusion you can see HP here, and SLS, EOS, Sintech kind of companies or the 3D systems are there. And DMLS and SLM, EOS, DMLS, SLM, Renisa, Concept Glacier, these are the companies. And EBM, Arcam comes here. And Lens, Laser Engineering Netshape, which is Optomec is the one of the major company. And EBAM, you can what's this? This company? Shike, yeah, Shike, correct. And LOAM. These are the companies also mentioned here in this slide. That's all. Now, VAT polymerization, if we go, there are 3 important technologies. Stereolithography, which is one of the oldest and widely accepted technology in plastic additive manufacturing. This particular technology in the initial stage developed by 3D systems. Later on, QWS and DWS and Farm Labs are the companies who are all producing machineries of stereolithography. And second is DLP. There are 3D systems and as well as Envision Tech, and CDLP, a company called Carbon and Envision Tech. These are the 3 things. Almost these three technologies are same, keeping photocurable polymer as a raw material. Energy source only differ. In SLE, laser source will be used as the energy source. The other two light sources will be used. So let us see stereolithography apparatus. This is one of the important and oldest and widely accepted, well-proven technology available in the additive market, largely used for initially it was used to produce photo model of using alternate materials, but now in the recent past, lot of material development happened here. So that range of materials are available according to the functional requirement. We can opt that particular material. But one of the disadvantage here, the material change from this VAT raw material tank is a little bit tedious process. If in case if the machine size is smaller, and the material change is easier. If you go for the bigger build platform size like Pro X 800 or Pro X 950, the total material content in Pro X 800 would be around 300 kgs, whereas the other one would be having nearly 500 kgs of a 10 material. So changing the material is the challenge. So usually all the service providers used to stick on some single material when the build platform sizes goes above Pro X 800. Whereas in the small printers like Project 6000 HD, earlier it was called as Viper, this machine is having build platform size of 250 cubic millimeter, where we can have range of material. The VAT can be easily, we can remove it and change it. We can have some additional 2-3 watts with different materials. So changing the material VAT is not a big challenge. Whereas while we are going for big machines, and that is one of the problem, or it is a little bit tedious process. Okay, so let us come to technology. Here you can see there is one elevator it is fixed with the built platform. This is the platform which was fixed with a moving piston here. So the blue color, whatever we are showing here, is the resin, UV curable resin, lesser curable. And this is a resin tank which I know built platform. This is with support of piston, and this is the elevator to support the movement. And energy source here, laser source, and this is the scanner which take the input from the CAD file here. So as we explained in the morning, while we are coming for application, the STL, the 3D model or the CAD model in STL format, stereolithography format, would be given as the input to the additive machine. The machine will be having two different processes. Production happens. So if you feed a drawing, orient is based on the build platform. For example, in the horizontal or vertical or a slide, the orientation
Yeah. You're audible, sir. Sir, can you? 2 minutes now, sir.
Hello? Could you able?
Now you are audible, sir. Yes, sir. Now you are audible.
Okay, okay, okay. I think from. Could you able to hear me now?
Yes, it's clear, sir. Yes, sir.
Yeah. Okay. I think this slide we can. The oldest widely accepted technology, which are very stated, the material. On the early stage, it would.
Hello. Sir, I can't hear you now, sir. Hello. Not all message. Hello, sir.
Hello.
Yes, sir. Sir. Yes, sir. Yes, you're audible. Can you hear?
வெறும் கேட்டுக்கலாம் அப்படின்ட்டு நம்ம வீட்டில் யாருக்கும் கொடுக்காதீங்க. அதை கழட்டு எல்லாம் பண்ணி குட்டி பண்ணி வச்சிருக்கீங்க. அவ்வளோ கிளீனாக இருந்தது. ஹலோ, இந்த மறுபடியும் வெளியில போயிட்டு உள்ள வந்துக்கலாங்களா? இங்க ஏதாவது மறுபடியும் ப்ராப்ளமா இருக்கு. ஓகே, ரைட்.
ஷேர் பண்ணி பாருங்க சார்.
சரி, ஷேர் பண்ணணுங்களா அப்போ மறுபடியும்? சரி,
ஆமாங்க.
இது போஸ்ட் பண்ணணும்.
நீங்க presentations
audio. Can you able to hear me?
You, but your presentation is not visible, sir. Yeah, it is coming now. Yes, sir. Your screen now.
Hello.
Yes, sir. Yes, we can see and we can hear you too.
Hello. Okay. Audio. Okay, right. Sorry for the difference actually. So the early stage, while the stereolithography was launched, there are options which were largely used for photo model development. The latter stage, a lot of material development happened for this segment. Now we have a material of different choices according to our functional requirement, maybe having flexibility or high strength or thermal requirement. So on that basis, you can opt easily for the stereolithography. The other big challenge in this thing is the material change, because every vat will be having a single material. When we change the material this into some other thing, then we have to remove this material, add the new material, or we have to have additional vats. Changing the material is quite easy in small machines like Polyjet 6000 HT and all, but it would be a little bit tedious in ProX 800 or ProX 950 cases. So that's one of the important things to be noted. And let us come to the technology. This apparatus will be having a moving platform, build platform, supported with piston and an elevator. There will be a small vat to have the liquid resin here. That means the raw material. And there is a laser source which should be used to polymerize the liquid resin, and there is the X-ray scanning mirror to get the 3D output inside the machine. There are the two important parts in this machine. One is software side, the other is the hardware, where the printing used to happen or the production used to happen. So while you are checking the CAD model in the STL format into the machine, we have to orient the part in a right manner in the platform. The orientation is the important criteria which we have to concentrate more, because this only will decide the cost and the final finishing of the product. So in case if you in a vertical way, it will consume more time, and the machine hour time would be increased. Indirectly, it will increase the project cost. And in case if you keep it in standing, and then there are the possibilities for the generation of more support material, which will end up with increase in the material consumption. Again, the cost of the project will go up. So we have to optimize in such a way to get the good surface finish with competitive cost. That by experience you can learn this. So once the orientation is done, then the next thing is the slicing. So automatically the slicing software will start slice your CAD data into number of layers. So here you will get option to fix up the layer thickness. In stereolithography, the thickness will start from 75 micron, and there are additive machines you can go up to 25 micron also. So, or you can go to even 200 microns also. So, depends upon the layer thickness, the surface finish varies. So, in case if you go for a fine layer, thin layer, you will get a highly smooth surface finish. And once if you go for a little bit thicker layers, then accordingly the surface roughness also will be more. So once the slicing is over, then the CAD data would be in a sliced manner now. So this scanner will take the input from the CAD data layer by layer, and it will be scanned by the laser. Directly, the laser will scan over the raw material. So the bottommost layer of the part would be taken in the initial stage, and that will be scanned over the platform here. So you just imagine the build platform in the topmost layer of the resin. There will be a thin layer only spread over this build platform. This is the build platform. Just imagine that it would be, I don't have a board here to explain you. So you can just imagine it would be the topmost layer, a thin layer of raw material resin will be spread over. The thickness of resin spread over the build platform is almost equal to the the layer thickness what we opt for the protection. So once the first layer of the information will be taken from the 3D model, the laser will scan over the build platform here. So wherever the profile is there, that area will be scanned over the resin. That particular portion, the resin will get polymerized or solidified. The rest of the area, the resin will be in the liquid form. Once the first layer solidification is over, the build platform moves down, yeah, equivalent to a layer thickness of what we opt. For example, if you opt 100 micron, this build platform moves down by 100 micron. Then first layer of, there will be a resin recoater would be here that will coat a fresh layer of resin over the build platform. Then layer information will be taken by the laser, scan over the platform. Wherever the laser falls, that area will get solidified. Like layer by layer, the solidification happens here. So that is the reason we call it as even a layer manufacturing. This process will go on till the completion of build of complete layer. In case if it is 300, 400 layers in the part, till completion of almost all the layer, this process will continue. So once the build process is over, the elevator bring the build platform to the topmost so that the pot can come out of the resin, and we have to leave the pot for some time to drain out all the liquid resin here. Then we can take out the pot, clean it with solvents like isopropanol, and then we can keep it inside a curing chamber again, a UV light-based curing chamber, to avoid the stickiness over the surface. So this is a process of stereolithography, and here usually we have materials equivalent to ABS, material equivalent to PC, and there are transparent material and material with high flexibility and material with high strength and material specifically produced to develop patterns for investment casting. So that is the different thing, because there instead of solid structure, a honeycomb structure would be developed. And so that honeycomb structure will facilitate easy burnout during the casting process. So the part, whatever the pattern produced in stereolithography, would be taken to shell molding or investment in the casting process. Or after once the cell mold development is over, as like as routine lost wax casting, it would be taken for burnout, as dewaxing and burnout. One after the burnout process is over, then we used to take it for the casting. So the casting may be the gravitational force or the vacuum casting, whatever the way. The rest of the process would be as same as the regular investment casting process. So that is the other advantage of stereolithography, and this also will be largely used to produce patents for the surgical reversals in the medical application. In case of any complicated cases, so the doctor used to have a proto model to conduct the reversal of the surgery and plan his surgery in a better way. So usually this technology is largely used for that application. And further, this is largely used in jewelry application also to produce patterns for casting. So in India, there is one service provider in Bombay using more than 8 to 10 machines only for the jewelry application. So that is the other advantage. And if you're coming to DLP, and same as stereolithography, and you can see here the source, energy source will be in the bottom side, and there will be a transparent screen which separates the light source and the raw material here. So you can see here this light source, it's basically UV light, UV curable resin. That earlier on what we have seen is the resin. Laser source will be used as the energy source here, whereas here UV light will be used as the energy source. So it's a UV curable resin. The rest of the things are the same like as SLA. So it's basically a wet polymerization. The liquid resin would be, photopolymer resin would be solidified with support of UV light. So that is the advantage, and you can see some of the machines which are available in the market. Envision Tech is one of the familiar company producing this digital light processing DLP technology machines. It's a very old company like as 3D Systems, having existence of more than 25 years. And in DLP, the advantage, you can go up to even 25 micron layer thickness, well suitable for jewelry application. Very thin layer also can be effectively produced, and very thin profile also can be easily generated in this one. So this is the digital light processing technology, and one next is the fusion material extrusion. Fusion deposition modeling is the one of the technology owned by Stratasys in the early stage. After once the patent was opened, there are a lot of players in this category. Ultimaker and MakerBot is the two important companies. These companies are producing tabletop printers. So here, not like as in wet polymerization, here the raw material would be in a thin filament form. So the filament will be extruded through the heating sources here, and this is you can see here this is the extrusion head where it gets liquefied, and it acts as a regular printer, like how our desktop 2D printer works. The same way, how our printer will take the input from CPU and print on your paper, the same way this printing head will take input from the CAD file and print on the build platform. So instead of printing ink there, here we use the liquid polymer. So the filament will come through the extruder and will get liquefied. So the liquid polymer will get injected or printed through the two printing nozzles, printing heads. Here you can see printing nozzles actually. Through that the material will be coming over here and built on the platform. If these two, one is meant for support material, the other is for the regular material. So this is a time to explain about the support. I think let us play this video. I will then explain about the support material. We are going to build a aircraft like this. So you can see here, this is the process of orientation. So a preferred vertical orientation. So you can see both the wings are not having any support. So this is slicing things are happening. So too many layers. Slicing is completed, and you can see here in both the wings there are support material generation. So it is essential for the elevated surfaces or elevated profiles to have support, or otherwise there will be possibility of warpage. So generally the support material will start built from the bottommost layer, and it will come up along with the main material, and wherever the any elevated profile comes, there it will give strength like as a scaffold. Just go through this video. Audio or not even? No audio.
So there is a checkbox, sir. When you are sharing this video, there will be a checkbox. In that, you will have a checkbox to click to say share audio.
Could you able to hear the audio in this video?
No, sir, we are not able to hear
Yep.
the audio. Sir, hello? Hello?
Hello? Anybody? Could you able to hear the audio?
Sir.
In this you can see here, this is the orientation. Then next stage is the slicing.
Hello, sir.
And next stage is the support generation to give support for the elevated profiles.
So audio is not.
Then tool path generation.
Hello, sir. Hello, sir. Sir, am I audible?
This is the process of tool path generation. So the information from the CAD model will be taken inside. And this filament goes through the hot rollers for extruders and get it liquefied. And you can see the moving print on the platform. And the white color, what you are seeing is the main model material. And whatever you are seeing brown color on both the sides of the wing is the support material, can be leached out after once the build is build is completed. So the support material generation is very, very important, or otherwise there will be possibility of deformation or warpage. Okay, so now, and you can see this is one of the machine, even what we have at our center here. It is F900, one of the biggest build platform of 900 by 600 by 900 mm. And you can see different kind of material options: 1, 2, 3, 4, 5, 6, 7, 8, 9, nearly 9 material options. So what we have 6 materials here, and you can able to achieve the accuracy of 0.1 mm here, though they are committing 0.089, and you can say 0.1 mm this thing. And the same status is having different kind of printers, more than some 10 kind of printers in the same category. And now next what we are going to see is the material jetting. And here you can see 3 different kind. One is cured with UV light, another is cured with heat, and another one is milled to form the final profile. So material jetting, Polyjet, basically you can see here, it's a Polyjet 3D printer. It's basically, there will be, you can see the parts of this one. There's a material container, ink print head, inkjet print head, and this is UV curing light. And again, the printed parts assembling here, and whatever support structure generation and everything, this is a build platform. So here, the raw material will be injected through the print head here, through the small nozzles in this print head, and it would be cured by UV curing light. So the first stage, the slicing, orientation, everything is common for all the technology. So once the slicing is over, the build happens here. The ink will be injected over the build platform. So wherever the profile there only the ink would be injected, and it would be simultaneously cured with support of UV light source. So this is the kind of material jetting technology. So Polyjet material properties vary, ranging from a rigid to flexible rubber. You can able to produce in a single build, and various colors also can be given in this. You can either produce the transparent part or solid colors with different shades, and you can able to produce rigid, and also you can able to produce highly rubber-like flexible parts. So even in the single build, you can able to build all together one particular part or profile in a transparent, the other one in a color with rigid material, the other one in a transparent water white color. All this thing in single build is possible. So this is a machine what we are talking about, J750, again from Stratasys. This has a build accuracy of 0.1 to 0.3 mm, and layer thickness you can go up to 0.016 mm. So any component of wall thickness of minimum 1 mm is essential to build in this, and the build dimension is 500 by 400 by 200. And there are another models also. You can go even up to 1800 by 500 also, bigger platform size. And some of the parts produced here you can see highly flexible and variable colors, largely used in shoe company to produce soles for the shoe, and to have a proto model development for the shoes. And medical application, it has got a lot of role. As you can see, the real human organs can be easily built at any transparency, and you can like how the hardness of tissues varies accordingly. The gray value can be generated, and you can vary the hardness, sore hardness of individual portions to make it highly flexible or rigid. That is the application. There is an advantage in this machine. So what are the advantages you can see here? In a single build, you can be able to produce a component with the profile requirement of flexible, rigid, color, and transparent. So this is the advantage of Polyjet. And next thing is a binder jetting. This is basically, a company called Vauxhall Jet is producing a machine under BJ, largely used for to produce solid core for sand casting requirement. Sand core can be easily produced here. So here it is nothing but a binder, a powder bed would be there. A binder will be injected from the printer. That means the build platform would be having a powder dispersed in a thin layer form, and the binder would be injected through a print head here. So wherever the profile recurs, there only the binder material will be injected. So the material, the binder will support to glue the particles together and act as adhesive. So this is largely used to produce sand cores and ceramic kind of pot manufacturing in for various applications. So the main advantage is the production of sand core for sand casting. So very big platform can be produced. You can go to build platform of even 1 meter also is quite possible in this. You can see this is one of the Germany-based company which is having. You can see the build space of 2000 by 1000 by 1000 mm in XYZ, and the layer thickness would be 250 to 400 micron, little bit higher since it is serving for the sand core application. So the slight surface roughness is not a big issue here. So build speed you can see 21.6 mm per hour. So this is largely used for sand core production. You can see a small pot here produced in this. Quite expensive machine. And the next thing is the powder bed fusion. Generally, we call it as multi-jet fusion. HP is the only company is producing this one. Here, the powder bed is common, and there will be two agents to be injected through jets. One is the fusing agent, which will fuse the powder together, and there will be a detailing agent, which will give you a final shape to the part resolution. That means to give a perfect shape and everything. Because while this fusing agent is injected, and it will spread over the powder. And perfection may not be that much clear here. So next is the detailing agent will be injected. That will give you a perfect resolution for the part. So the lamps will pass through again. UV lamps will give. Sorry, I think IR lamps here. Here, no. IR lamps. Yeah. So infrared lamps would be passed over here, so that to give a perfect polymerization or fusion process. Okay. And next is the powder bed fusion. There are two categories: SLS for plastic and DMLS, SLM and EBM. All comes under for the this thing metal side. And SLS, you can see this is the moving bed, like as SLA only, with support of piston. The build platform can be moved up and down, and the powder will be spread over the build platform, and there will be laser source in the top of the machine. Rest of the process, like giving CAD input, slicing, taking the scanning the CAD data, and this laser will scan on the powder. So in stereolithography, the laser will scan over a liquid resin, and wherever the laser scans that area, the resin will get solidified. Whereas here, the laser will scan over the powder, whatever spread over the platform. So wherever the profile is there, that area it scans, that particular area of fusion happens, or the particles merge together, or we can say the polymerization happens, and the rest of the area, the powder will be in a powder form only. So that's the advantage of this technology. The uncured powder will act as a support material. No additional support generation happens here. So in SLS, largely nylon-based materials are used for different application. And you can see here, this is a powder spreader, spreads the powder, and you can see the laser will scan over the build platform. You know, that scanning building is over, the platform moves down. A fresh layer of powder will be spread over. The next layer of scanning is happening and polymerization is happening. Like this process will be repeating till completion of the final layer. So this is a laser source, this is a powder spreader, recoater, or this is a piston supported build platform. You can see here the powder will be, again, it's a recoater, powder spreads, and this laser scans over. Wherever the profile is there, that area the powder will get polymerized or fused. This is the case of selective laser sintering. And you can see the UV is missing of SLS. Originally, this technology was developed to be DTM, and later on, a lot of companies started producing machines under this. A build platform size of 340 by 600 mm, and we can recoating, double recoating system. That means you have seen, no, the recoating comes from left and right both together. And there's other SLM, laser-based selective laser melting for metal. This is a company called SLM Technology, produces metal machines for various applications. Here, laser will be used as the energy source, little bit high power energy. You can see here the laser power will be 70 watts. Carbon dioxide based laser is used here. Whereas here, the laser power is in 400 watts. Sometimes it may be in 1 kilowatt or 2 kilowatt. You can see here quad 4 into 400 watts here. So to increase the energy level of the source, so that the build speed can be enhanced, and that's advantage what we will get here. So either you can use 2 into 400 watts laser, IPG fiber laser, or 4 into 400. 2 into 400 will be a little bit slow than compared to quad 1. And this is largely used for metal application. So to melt the metal particles, ultimately, definitely we have to have high energy source. That's the reason we are using 400 watts laser here. Again, the double-side recoater, everything is quite common, like as the SLS only. And this is EBM, one of the wonderful technology used largely for aerospace and medical application. As I said in the morning, this technology was owned by a company called Orcam, later over taken over by GE. And high energy source of electron beam here, minimum of 3000 watts. So that the pod built with this thing will be having the temperature gradient is used to be completely eliminated. So the residual stress of the board built in this technology comparatively low when we compare with the laser DMLS or DED kind of technologies. So fully dense parts will be produced here. Largely, we can use the material called titanium, cobalt, chromium, and inconel. These are the three materials largely used in EBM. The same way, SLM is having a range of material options. Different kind of material. You can use stainless steel, maraging steel, tool steel, aluminum, inconel, and titanium. So compared to EBM, either SLM or DMLS is having a range of material options. That's the advantage of other technologies. Whereas EBM at present has only limited materials, titanium 2 grades, inconel 2 grades, and cobalt chromium for medical application. And recently they introduced precious metals also under this category, but still not commercialized, like a silver and gold and all also been uh, used here. This is a small video about electron beam melting technology.
Hello, sir. Hello, sir. No, sir. Sir?
So it's a electron beam based one. The model called Spectra H, a very big machine. As I have told you in the morning, this machine is having a lot of advantage. One is the whole build process happens in vacuum. I will just play the video once again, so that possibilities for contaminations can be completely eliminated. So recoater spreads the powder over the build platform. Both the ends will be having a material storage. So this one's this energy source kept here. So the electron beam is the energy source. 6 kilowatt beam, you can see here it fuse the powder like in build speed is compared to other thing 50% faster than the other thing. So it's a quite big build platform. You can see the turbine blades built in this machine. So GE is a titanium aluminide based. Removing the belt from the machine and taking to the recovery unit where the uncured powder and all will be removed, and you can see here removing the uncured powder, and it would be recycled and collected because the powder is quite expensive, and moreover it's harmful to the human health also. If you inhale this powder, will get settled in the lungs and give a lot of health complications. So better to recover it in a proper way. There will be a vacuum to get the uncured powder, and it would be taken for the rebottling again. So that will be kept for the rebottling again. Actually, so this is a really wonderful technology. The history behind this technology: The RCAM developed this technology way back to early 2000, maybe in 2001-2, and they started marketing this machine to the global level. It is really wonderful technology, not well received in that time by the industries. And GE procured one machine and started using to produce some valve system for the aerospace requirement, specifically for their aero engine build process. But after seeing the capability of the machine, they developed their own material called titanium aluminide, and they patented that material. Using this titanium aluminide, they developed a range of components for aerospace requirements, and they started buying one by one more than somewhat around 30 machines from Arcam. And one fine day, they have taken over the company by themselves. Now it is a GE-owned company. And the advantage, you can see here, build platform of cylindrical platform of 350 dia and 380 height. 3000 watts electron beam, energy source, and you can see here translation speed is huge, fast building compared to laser based machines of 2 laser. And see here some of the components produced in EBM. This is hip joints. This is knee requirement, some sort of customization. This is a spinal cord requirements. And these two are the aerospace components. And the next thing is the direct energy. Here you might have seen yeah. So here you can see the energy source comes from the top, and there will be two powder storage units. From there, the powder will be spread over the platform here. So the material will be spread over the build platform. The energy will come from the top and scan over this powder surface, and wherever it falls, that area will melt and merge together. And once the particular air build is over, this build platform moves down. From the hooper, the additional power will be taken over and spread over the surface by the powder spreader. So this is the kind of thing where the energy source comes from the top. Whereas here you can see there are the laser source comes from one side, the energy source, and material will be sent from the two nozzles, or 2 or 3, whatever. That's the advantage here. You can use multiple material. So the material will come from this other side. The laser will falls on that. So here it will get solidified, liquefied and melt together. So this is a process. So here the advantage, for example, if any component is having more than 200 mm thickness, so 50 mm we can build with one material, and another 25 mm if you want to add some other material in between, and that also is possible. So that's a advantage here. So it's called direct energy deposition. This is a kind of technology. Even the PhD also in attempt to manufacture a machine, indigenous machine, with support of DST. So it's basically laser source based. So DED, Optomec is the one of the company which produces DED machines. And the advantage of DED is you can have a very big build platform. Like as you can see here, 600 400 by 400, 800 600 by 600. Whereas in either in DMLS or EBM, maximum of 350 400 mm is the build platform. Maybe in SLM recently they launched one machine with around 600 mm cubic built volume. So that is recently launched, quite expensive. So this is the direct energy deposition machine. And you can see here the material chart for various metal EM technologies. Titanium, largely used in laser powder bed fusion machines, and even electron beam powder based bed fusion also. On titanium aluminide is possible only in EBM, cobalt chrome is possible in both laser and EBM machines. Tool steel is possible in a laser machine. Stainless is possible in laser machine. Inconel is possible in both the machines. Aluminum is possible in laser machine. Copper is possible in both the machines. Tungsten is possible in laser machine, and precious metal is possible in laser, and even EBM is also recently proved that they can also. So if you see here the material, one side you can see the different kind of materials largely used in metal additive manufacturing. You can see a titanium 2 grades, grade 2 and 5, and titanium aluminide specifically for aerospace, and cobalt chrome both for engineering and as well as medical application. Generally, knee joints are largely produced with support of cobalt chromium because of its high strength, but have high dents also. So the implants produced with cobalt chromium will be having more weight compared to the titanium one. Depends upon the requirement. The knee joint is largely produced with cobalt chrome. Rest of the either hip joint or any craniofacial and maxillofacial or customized implants and all, largely titanium is used. And tool steel for engineering application is laser based. And stainless steel, you can see 3 different kind of thing, all used in laser only. The acceptance of stainless steel, some of the EBM users are tried and unofficially they started using stainless steel for their application. But officially, GE is not committing on stainless steel material. And Inconel is quite largely used in aerospace requirement, nickel superalloys for the various applications in aerospace and defense segment. So both the technologies are accepting this material. The aluminum is possible only in laser machine, and copper and bronze accepted by both the machines, and rest of the things are accepted by only laser machine. So these are some of the material list you can keep in mind that most of the metal additive manufacturing machines are using. And now we go to the next level, metal how been used effectively for the application. You can see here the first one, a part produced by GE is assembly of more than 20 parts. A single unit is having assembly of 20 parts, so it's all individually made and assembled together to get this part. So whereas in additive, this one, the additive, you can produce this as a single component. So the number of components can be reduced in additive manufacturing. That's one of the good advantage. In one way, you can reduce the inventory. The other way, you can be able to reduce the complication of assembling too many parts. So that is one of the biggest advantage of additive manufacturing, specifically in metal side. So GE started producing this kind of aerospace components by using EBM. So that's I think this particular valve system was produced by GE for aerospace requirement with titanium aluminide, and this is serving to the healthcare segment. This is a knee joint, knee cup actually. Sorry, hip joint, and this also a hip only, and this is some sort of maxillofacial requirement, a customized implant, a little bit complication. Most of our medical requirements at present we are importing. More than 98% of our medical implants have been imported from different part of the world, and United States of America, and to some extent Germany and UK. They are all commercially producing 3D printed implants, and concerned authorized centers, FDA approval, generally we call it as American FDA, had given approval to use EBM technologies in implant manufacturing. The reason they quoted was again what I have told was that the complete build happens in vacuum atmosphere, minimizing the possibilities for contamination. And the rest of the things you can see here, maxillofacial requirements, all customized implants can be easily produced in additive, because the conventional manufacturing will not give such a kind of timely and as well as perfect support like additive for customized implants manufacturing. And this is in automobile side. This kind of complex features can be easily printed. And turbo intercoolers, this also by using aluminum. This all printed in EOS machine, and this challenge in conventional methodology can be easily produced in additive. And tuning industry is also getting more benefited from additives, specifically laser-based machine, the two DMLS and SLM. This is probably we all know about the conformal cooling channels. Will be provided inside the tool to increase the productivity. That means to increase the solidification of the plastic injection part, so that the cycles can be increased. So this kind of critical channels can be easily generated in laser-based machine, and this supports to increase the injection cycles, and the timing for the solidification of the injected plastic parts can be reduced to 60 to 70% with almost no scrap. That's what the other advantage. So here, additive is finding good application, and this is the topology optimization. In topology optimization, you can see here, this is a roller component for regular application, and how we have optimized the design in such a way to reduce the material consumption without affecting its functional importance. So this is a development of optimizing the topology in such a way to reduce the material consumption, to reduce the weight. This will give more advantage for the aerospace segment. You can see on the other side how the combination of topology optimization and metal additive will give good results for the aerospace segment. And it's how the 3D printing can be largely used in medical application. This is a scan data, CT scan data. DICOM images will be received from the scan data, and it will be converted into STL, and that will be printed like this and can be used for surgical practice. I'm just disclosing one case example here. This is a case we have done at PhD Typhocor in 2003 in collaboration with KMCH Hospital in Coimbatore. The person met with an accident. You can see the damage in the skull. In fact, there is no material. I think the radiograph shows the clear thing. The skull, the red portion, shows that there is no skull material. And usually doctors follow autologous rib graft kind of technology. That means the ribs from the same human body would be removed, and that would be split like this, and it would be spread over like this and close with the skin. So this is the ribs inserted below calvary edge, and it will be close with the skin. This is a methodology the medical industry used to follow, and this probably the first surgery in India. I can say the first case in the country, first surgery performed at KMCH with support of AG Typhocor using additive effectively for the surgery case. So this is a case, you can see here the real damage, the skull. Generally, they call it as temporal cranial defect. This definitely need a surgery, a kind of maxillofacial kind of thing. So here, the doctor in 2003, there was no much development in additive, and as well as in the other implant side also. So one doctor had associated with the typhoid code, so he could able to give a CT scan data of the defective skull, and that here a engineer in association with doctor developed a 3D CAD model by using imageware software, matching to fill this gap whatever find here in skull. So it was a designed one with a variable thickness as per the guidance given by the doctor. Accordingly, the thickness being given, a CAD model was generated, not like a CT scan converted into the STL format. So that kind of possibilities are there now, but in those days, this was not there. So this was used as the input to produce the part from FDM by using ABS material. But unfortunately, this cannot be directly used for the surgery because it's not a biocompatible material. So using this as a template, doctor has he has imported a material, PMMA, polymethyl methacrylate, a biocompatible material, and a silicon mold, a soft mold was developed using this pattern, and this processing, the PMMA material was developed accordingly, and this was successfully used for the application. You can see here the surgery planning incision, and the defect was clearly exposed. There is no skull here, and the doctor is doing planning. That means keeping this PMMA material inside and fixing this with titanium screw, positioning it, drilling on the skull, and positioning like this. This is a final fixation. And the lateral radiograph has confirmed the presence of implant inside. And this is the case prior to surgery and after post-surgery. And these kind of things give a lot of advantage over the conventional one. The regular rib, you can see here, the rib would be removed from the same human body at different parts. Generally autologous rig graft. So here, the post-surgery problem would be more. The secondary infection, generally we call it as, probably the skull problem would be solved, but the ribs where we remove from the other part of the body, where the infection starts, secondary infections. So post-surgery problems was completely eliminated, and the fixation was perfect, and the patient was doing well. So this is advantage. Maybe this was the first case in India in 2003 with support of additive manufacturing. And this is the skull of a 10-month baby produced for one of the familiar hospital in Coimbatore. This baby was having some twisted head kind of issue. That means once the baby grows, our body part should grow proportionally. There was some restriction in growth of the skull. So it was essential to have a surgery. Since comparing the age, a 10-month-old baby, and the doctor was so careful, would like to have a reversal to open this head with conducting the surgery and planning it well. So we produced a 3D output for that and given opportunity. More than 8 doctors involved in this surgery, and doctor conducted the surgery over the skull and procedure for the surgery, and it was 100% successful one. And this is the lower jaw panel for the maxillofacial kind of recombinant. See, this is the lower jaw of the accident. The person met with an accident. You can see the lower jaw was damaged. Some material is not there. but the doctor would like to go for a maxillofacial kind of a command, but the patient wants to retain the same flow here on his lower jaw. So doctor used titanium strip. This was 3D printed in SLA, and the defected portion CT data was taken and printed. And using titanium strip, they have taken only the flow here, and then they have gone for the rib graft, removed the ribs from the same human body, and it was stick over this titanium strip. Since titanium is a biocompatible, it can be easily incorporated inside the human body. So along with this rib, this was positioned inside the human lower jaw, and this was the case supported for an hospital in Europe. And this is a different stage. And this is my medical modeling of heart. Cadaver systems availability is so scarce is now. Very tough to get cadavers for the medical students for their regular practical classes. Maybe one cadaver system would be shared by more than 3 or 4 students. And keeping that as a objective, we are in the process of producing in the initial stage various organs in additive manufacturing and giving to students to conduct their practicals over that. Generally, they used to cut into 2 or 3 parts and do their studies. So that we have produced a synthetic cot, and still some developments required that is going on. And this is a biomedical modeling, a case of thyroid. A tumor is inside, in between lungs, liver, and heart. A 14-year-old boy had this problem. He had a tumor of around 140 mm size, and he could not able to breathe well. So since this tumor was touching all the 3 important organs, the surgery was so complicated. So the doctor would like to have a proto model of this case, to have a rehearsal. And this part was produced, and successfully the surgery was done at PAG hospital. This was the quite charitable one, solved by Additive. And this is the trachea which I have told you in the morning. Generally, the doctor, when we go for gastroenterology kind of problem, they used to do endoscopy or brachostomy actually. That means the camera will be inserted through our trachea. All interior things they used to analyze if any defects are there inside. So usually doctors will not get opportunity to train apart from the human body. So usually the patient will be treated as the real patient will be taken as a training model there. So the fresh doctors used to insert camera wrongly, that will hurt the patient and painful to the patient. So to avoid such a kind of thing, we have taken a CT data of trachea and produced a 3D output like this. So here they can enter the camera inside. We can study about all the issues inside the trachea. So this will just give training to the doctor how to handle this instrument inside the trachea. So you hear all these branches they want to see. So they cannot open and do that. So with the real patient they used to do. So by experience they have to move the camera inside the various parts of critical parts of trachea. So this was produced in Additive machine, and this advantage the Additive give for the hospital segment: improved visualization, communication, regressive, and pattern confirmation of implant materials. So these are the various stages we have covered here. Probably I might have covered various technologies and their application in plastic and as well as metal. Time is too short. With this, we have to give all the application and technology also together. Hopefully, I have had a good thing to you. In case of any question, probably I am not able to hear your voices, and you can just send the chart to me here.
Sir, what sort of materials do we implement in medical industry for 3D printing?
Hello.
Hello.
Any question?
Sir, what sort of material do we implement in medical industry for fabricating the tracks and all?
Dear participant, sorry, Sridhar sir has some technical issue. Maybe you can type your query in the chat box. That will be better. Please do this. Hello, sir.
முடிஞ்சதுங்க பட் இது எங்க வாய்ஸ் நீங்க பேசுறது கேட்க மாட்டேங்குது. ஓகே 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 ஓகே.
So the participant, if you can give the name, I can type your name also along with it.
See, the first question is the trachea model is printed using which polymer? It's basically by using Polyjet machine J750. Yep. Called Vero Clear. It's basically PC kind of material, and this particular machine, what it will do, it will take 3-4 different kind of polymers together according to the stored hardness, whatever we record, we have to feed. So according to the stored hardness, what we are sending as the requirement, the material will be mixed with itself, and the polymer output comes. So generally PC is largely used for this kind of application. And second question, what material is used for medical application? Generally for implants, we follow titanium based alloys are used largely for implants. Now for hip joints and maxillofacial and customized implants for different bodies, maybe in the lower jaw or other leg, hand, all these areas. But for the knee joint specifically, cobaltomium is recommended strongly because of its high dense and high strength. The printing materials that are available in making trachea and other medical application. That's what I have told you now. One Mr. Dr. Vamsi Krishna Chandru. So the same question I have answered. It is basically a combination of 2-3 materials in J750 machine of Staticis. It's a kind of polymer, proprietorship material. They don't disclose, but it is a kind of flexible rubber kind of material is used. 3-4 material in this machine. As I told you, we can produce rigid as well as the flexible parts. So according to our requirement, the material will be mixed together. So that kind of material is used for trachea building. So how to validate the quality of 3D printing, whether the 3D printers does that job also. Validation of quality of 3D printing, that depends upon the requirement. For example, if you talk about plastic additive manufacturing, 3D printing, you can compare with the FDM and SLA, stereolithography and fused deposition modeling. Stereolithography models will get good surface finishing, and minute profile realization is quite possible in stereolithography, but strength-wise, it will not match to FDM. Whenever any functional proto requirements comes, FDM will give good results than stereolithography. So the quality depends upon the functional requirements or other specific requirement of the client. So validation of quality of parts produced in 3D printing depends upon their individual requirements only. So depends upon that we have to opt for the technology. In case if I need good surface finishing, I have a very minute profiles, then I have to opt for stereolithography. In case I'm producing an enclosure for one mechanical system where I need more strength and assembly, then I can opt for FDM. So that it depends upon the technology. The process of jewelry, I think Mr. K. Palaksha Reddy, his question was how the process of jewelry 3D printing happens. For example, in jewelry, probably you may outsource the design from the designers in a pencil sketches form. That pencil sketch you have to convert into 3D format, CAD format, by using a software called Rhino. It can be effectively used here. So once the 3D model is ready, then you can send it to any service provider. He will get the 3D printed castable part to you. So that one you can take it for casting, replace your wax, you can assemble this one in your wax tree and do the investment, do regular dewaxing, burnout process, melt, do the casting as per the regular casting process. So here you have to do conversion of your 2D drawing into 3D and then sending it for the printing in a with the material of castable material. Then you have to do the regular casting. Is it possible to create 40 micron holes in SLA? Little bit tedious. Though the company is telling 25 micron and all possible, it was possible to 100 microns holes is possible. Less than that is quite challenge. How do we get the certified quality of human organs made of 3D printing? Organs, it to come. A lot of developments are happening in the organ with bioplotter kind of thing, because it's all involved with tissue engineering also. So a lot of developments in the global level additive manufacturing is happening. It takes quite some time. So now it's only for the implants it is available, specifically for the orthopedic implants, where metal additive machines are largely used. In case of study of defective skull instead of the ABS, why not metallic material like titanium is preferred used? The titanium and all been introduced in the recent past. When this case was attended in 2003, there was no metal additive manufacturing for the medical implants manufacturing. And also awareness in the additive side also very limited. The technology was limited, and accessibility to the technology also very limited. So there is no option other than going for this kind of producing ABS polymer material and using that as the template and going for the PMMA plastic material, a biocompatible plastic material. Nowadays, titanium is the good option. You can go for titanium. NDT methods for metal parts made through. You can go for a regular thing, whatever we are following for casting outputs, like radiography or something like that. You can regular casting outputs, what methodology you are using, the same thing we can use for AM also. Hope Mr. Palaksha Reddy, your question is answered. Any preferred library for TICOM files? Standard human parts, it might be available. Usually, it's a practice. We have to go to hospital, getting the, sharing the information from the hospital to this kind of application itself is a big task, because every hospital will be having their own system. There will be a committee. What is the name? Ethical committee clearance is very important from individual medical institution. So it is not possible to get the DICAM readily available images, but though this kind of things are available on website, which would be taken from a general human being. But what we are doing are all patient specific cases where the DICAM images will be shared to us with a lot of confidentiality agreements. So whether printed skull may hurt or damage the brain, no. it will not disturb the HUD because the allowance would be given according to real skull requirement. It will not hurt the internal parts of the head. Hope the question of Mr. Parani was answered.
Sir, participants, do you
Anything
have any
else?
questions? Participants, do
Okay,
you have
thank you, Mr. Palani. And hope we can conclude.
Dear participants, I think we will conclude this session because if you have any queries, you can forward it to us and we will forward it to Sridhar sir. Or I think he's typing his mail ID. Probably you can contact him through his mail ID.
Hope we can conclude now. Thank you very much for the opportunity given to me. And in case of any requirement for the research support or any kind of workshop, kind of collaboration, you can contact at my specified email ID, what I have given here in the chat box. Thank you.
Thank you. Thank you so much, sir. I know that it is not audible to you, but participants, thank you for your patient listening. I hope most of your queries have been answered, and I can see that the session has been lively with too many questions. And I suppose you have taken up your fill. So today's session will conclude here. We will have tomorrow's session start at 9:45, and please join us 5 minutes before. And we will see to it that we check all the technical difficulties we face today. And we will try and
it's great.